This video will explore thin lenses, focusing on their types, terminology, and how to draw ray diagrams. Lenses are curved, transparent materials found in tools like microscopes, telescopes, and cameras. They refract light in a predictable and useful way, and are usually made of glass or hard plastic. The shape of a lens determines if light rays diverge or converge as they pass through. Lenses are essential for magnifying images or projecting them onto a screen. The image produced by a thin lens can be real or virtual, inverted or upright, and larger or smaller relative to the object. In lens terminology, the principal axis is an imaginary line perpendicular to the lens surfaces through the optical center. The axis of symmetry is a vertical line through the optical center. Both types of lenses have two principal focuses. The focal point where light focuses or appears to diverge is symbolized by F, and the focal point on the opposite side is F'. The focal length, denoted by F, is the distance from the axis of symmetry to the principal focus along the principal axis. Both types of thin lenses have two equal focal lengths. A ray diagram helps predict and understand how images form after light rays emerge from a lens. The index of refraction of a lens is greater than that of air. Light rays bend or refract toward the normal when entering the lens, and bend away from the normal when leaving it. Thus, light rays undergo two refractions upon entering and leaving the lens. A thin lens has a thickness small compared to its focal length, like an eyeglass lens. To simplify ray diagrams, we assume all refraction occurs at the axis of symmetry. A diverging lens, or concave lens, is thinner in the center. Parallel light rays refract away from the principal axis, diverging so they never meet. The resulting image is always upright, virtual, and smaller than the object. To locate the image in a concave lens ray diagram, you can use any two of these rays. A ray parallel to the axis refracts through F, a ray through F' refracts parallel to the axis, or a ray through the optical center goes straight. This diagram shows the three primary rays used to locate the image for a concave lens. The image formed is smaller, upright, located in front of F, and virtual. Concave lenses produce images that are always smaller and upright, regardless of object distance. Their diverging properties are used in items like eyeglasses and telescopes, often combined with converging lenses. A converging lens, or convex lens, is thicker at the center. Parallel light rays refract toward the principal axis, crossing at the focal point. These lenses are frequently used as magnifying glasses. Convex lenses can form a real image on a screen, but the screen must be placed exactly where the light rays converge. When rays from every point of the object hit the screen, a complete image is formed. To draw a convex lens ray diagram, use these steps. First, a ray parallel to the principal axis is refracted through the principal focus, F. Second, a ray through the secondary principal focus, F', refracts parallel to the principal axis. The third ray passes through the optical center and goes straight through without bending. You only need two rays to locate an image. The third acts as a check. When the object is between 2F' and F', the image is larger, inverted, behind 2F, and real. When the object is beyond 2F', the resulting image is smaller, inverted, located between F and 2F, and is real. The three steps for drawing the rays remain the same. If the object is placed precisely at 2F', the image formed is the same size as the object, inverted, located at 2F, and real. The three key rays are still used to locate the image. When the object is placed at F', the refracted rays emerge parallel to each other. Consequently, no image is formed. When the object is in front of F', the image is larger, upright, behind 2F', and virtual. This situation is similar to using a magnifying glass. Convex lenses, also known as converging lenses, are used for various applications such as magnifying glasses, cameras, and in corrective eyewear for farsightedness. Please work on the lens ray diagram problems and hand them in.